Good morning, students. So after 2 days break again, we will start the coordination chemistry. We started this chapter, and in this chapter, what is meant by coordination compounds, what is meant by coordination chemistry, how the nomenclature system is developed, how the names are given, what is meant by ligands, what is the types of ligands, then we discussed the nomenclature rules, how the nomenclature of coordination compounds is done. So this part is already completed. I hope you are doing the practice of the nomenclature. Also, I have given in the last lecture. This is already explained what is meant by anionic ligands and cationic ligands, how the names of the coordination compounds is given. Some exercises also I have given. I hope you completed this exercise. So last lecture, we completed this part. This is very, very important for the NEET, CET and board exam also. So today we will start the next part, that is effective atomic number. Note, many times this question is asked for board exams for 2 marks. So make a note in your notebook also, and your textbook also, make a mark there. This question is always asked for 2 marks, effective atomic number, and the short form is EAN. This is a EAN. E stands for effective, A stands for atomic, and N stands for number. So what is this EAN? I will explain. It is nothing but the total number of electrons only, remember. So I think in 2017 or 18, one MCQ was asked for the board exam. EAN indicates what? Dot, dot, dot. So it is nothing but the total number of electrons, remember. Effective atomic number is nothing but the total number of electrons, where these are present around the central metal atom or ion in the complex. So this EAN is nothing but it is the only the total number of electrons which are present around the central metal atom in a complex. So this is a calculated by one formula. I will give this formula. So this formula is EAN is equal to Z minus X plus Y. We have to remember this formula. By using this formula, you can calculate the effective atomic number. So I will explain one by one what is this Z, what is this X, and what is this Y. So one by one, I will explain what is this Z. So this Z indicates it is the atomic number of the metal. What is the Z? Z is nothing but the atomic number of the metal. Now I will explain what is meant by this X. So this X indicates what? See, X means it is nothing but the number of electrons lost. See, this is very important. Number of electrons lost when during the formation of the metal and during the formation of the metal ion from its atom. For example, Fe is there and Fe2 plus ion is formed. So here X will be 2. We will discuss the examples also. But before the examples, you should know what is meant by this Z, X and Y. If you remember this formula, we will get 2 marks for the board exam. So Z is completed. Z is nothing but the atomic number of the metal. X is number of electrons lost during the formation of metal ion from its atom. And then what is Y? Y indicates it is the number of electrons donated by the ligands. So what is this Y? Y indicates number of ligands. Number of electrons donated by the ligands. Now we will take one example. We will discuss what is EAN rule first. After this EAN rule, we will take the example how to calculate the effective atomic number. So what is this EAN rule? This rule is asked for 1 mark for the board exam. So listen carefully. What is this EAN rule? Again, EAN is effective atomic number rule. You understand what is mean by EAN? EAN is nothing but the total number of electrons around the central metal atom or ion in the complex. And what is this rule? Rule is different. So a metal ion, see what is this rule? A metal ion continues to accept electron pairs from the ligands. Means metal, which is a central metal atom in a complex, which accepts the electron pair from the ligands till the total number of electrons present around the central metal atom in a complex becomes equal to the atomic number of the next noble gas atom. I will explain in simple words. Listen. So what is this EAN rule? EAN rule means in the complex, you know, there is a central metal atom is there and the ligands are surrounded by the central metal atom, and this is a structure of any coordination compound. So what is this EAN rule? EAN rule means the central metal atom continues to accept the electrons pairs from the ligands. कब तक ये electron pair accept करेंगे? जब तक when the total number of electrons is equal to the atomic number of the next noble gas atom. Means a central metal atom जब तक इलेक्ट्रॉन कब तक इलेक्ट्रॉन पेयर एक्सेप्ट करेगा तब तक उसका जो एटॉमिक नंबर है उसके बाद मींस जो सेंट्रल मेटल एटम है उसके बाद आने वाला जो रियर गैस है उसका और उसका नंबर जब तक मैच नहीं होता तब तक वो इलेक्ट्रॉन पेयर एक्सेप्ट करता है. So I will give one example, then we will understand. So some EANs are effective atomic numbers are given. See, so if the EAN is equal to 18, 18 is the atomic number of the argon, 36 is the atomic number of krypton, 54 is the atomic number of xenon. All these are rare gases, and 86 is the atomic number of radon. So we will take one example, then we will understand. So see, this is metals. निकेल निकेल के बाद जो रेयर गैस आता है that is 36 which is the krypton because you know the atomic number of nickel C is 28. And what is this EAN rule? EAN rule is nothing but this nickel tends to accept the electron pair from the ligands कब तक जब तक उसका total number of electrons ये next rear gas जो 36 है 36 जब तक नहीं होता तब तक वो इलेक्ट्रॉन पेयर एक्सेप्ट करते हैं. दिस इज EAN rule. So I will explain these examples. So these are the some examples I have given. This is a complex C. This is nickel and tetracarbonyl. This is nickel tetracarbonyl. According to this formula, what is this formula? EAN is equal to Z minus X plus Y. So according to this formula, we will calculate the effective atomic number. See, so this nickel, see in this nickel, this is atomic number is Z is 28, 0, X is nothing but the electron pairs. When the nickel forms Ni2 plus or Ni3 plus or Ni0. So here is Ni0, so it is X is 0 here. See. X is 0 because nickel didn't lose any electron for the formation of ion. Y indicates 8. Why this is 8? Because there are 4 carbonyl ligands. One ligand donates 2 electrons. So the total number of electrons are 8. So why this this is 8? Because as there is a 4 carbonyl ligands, we can see clearly 4 carbonyl ligands are there. So these will lose how many electrons? 8 electrons will be lost. So this is 28, 0 and 8. We will after calculation we will get here 36 is a effective atomic number. So this 36 is the atomic number of the rare gas argon. So the EAN rule is satisfied here. Means this nickel will accept the electron pairs from this carbonyl ligand. कब तक ये accept करेंगे electron pair? जब तक उसका number 36 नहीं होता तब तक ये electron pair accept करेंगे. This is the EAN rule. So all these examples are given. The second example is Fe CN6 4 minus. See, Fe is the central metal. Atomic number is 26. Now see here X is 2. Why X is 2? Because here see the coordination oxidation state of this Fe is 2, because this is 6 minus and this is 4. 6 minus 4 is equal to 2. So the oxidation state of Fe is 2 plus. So these 2 electrons are lost when the formation of Fe2 plus ion. So X is 2 and Y is 12. Why this is 12? Because 6 cyanide ligand, 6 into 2. So it is 12. Again, we will discuss this example. CO atomic number is 27. NH3 is a neutral ligand, so 6 into 0, it will be 0. Oxidation state of cobalt is +3. So when cobalt 3 plus is formed, the 3 electrons are lost, so X is 3 and Y is 12 because 6 ammonia ligands are there. One ligand donates 2 electrons, so the total number of electrons are 12 electrons. So again, there is a effective atomic number is 36. So at the time of board exam, any one example out of these examples will be asked, and there are some also exceptions for this effective atomic number. So I will explain this one example. See, in this example we can clearly understand. Consider this example: CONH3 6 3 plus. So see, in this example, oxidation state of cobalt is +3. Why it is +3? Because 6 into 0, NH3 is a neutral ligand. So the oxidation state of cobalt is +3. And 6 ligands donate 12 electrons. See, 6 ammonia ligands are there. So the value of Z is 27. 27 is atomic number of cobalt is 27. X is 3 because 3 electrons are lost for the formation of cobalt 3 plus, and Y is equal to 12. This 12 indicates the 12 electrons. 6 ligand donates 12 electrons. So according to this formula, Z minus X plus Y, Z is 27 minus 3 plus this 12 is equal to 36. So EAN rule is obeyed. Effective atomic rule is obeyed by this complex. Then we will discuss the second example, FeCN6. These are the previous examples, only in detail I have shown here. I will explain this example. Oxidation state of Fe is +2 here. Why it is +2? Because 6 minus 6 cyanides, 6 cyanides having -1. So these will be -6, and when this 4 comes into this side, it will be +2. This is already I explained how to calculate the oxidation state of a metal, and this is very important. So as it is Fe +2, the value of X is 2, atomic number of ion is 26, and this Y is equal to 12. Why this is 12? Because there are 6 ligands which donate 12 electrons. Simple, we have to do the numerical, this mathematical processes. 26 minus 2 plus 12 is equal to 36. So effective atomic number rule is obeyed here. 36 means EAN rule is obeyed. Now consider this example. Yes. Consider this example. Zn NH3 4 2 plus. Here see the atomic number of zinc is 30. X is 2 here. Why X is 2? Because this is again neutral ligand. This ammonia is neutral ligand. So 4 into 0, it will be 0. So the charge on the complex is +2. So X is +2. Zn forms Zn2. So these 2 electrons will be lost. And Y is equal to 8 because 4 ligands are there. Wait for 1 minute. Yes. So according to this formula, EAN of Zn2 plus is equal to Z minus X plus Y. This Z is atomic number of the zinc is 30 minus 2. X is 2. Why X is 2? Because here the oxidation state of zinc is +2. So the value of X is 2, and This 8 is how many ligands are there? 4 ammonia ligands are there. So these 4 ammonia ligands will donate 8 electrons. So the EAN rule is obeyed in these all examples. Now we will see there are some complexes which do not obey the effective atomic number rule. So which are these complex we will discuss? See these complexes: FeCN6 3 minus, then CuNH3 4 2 plus. These having the effective atomic number is 35, which is not equal to the inert gas. So these are exceptional cases for the effective atomic number, and these exceptions are very important. Remember, in your textbook 1, 2, 3 exceptions are given. So these 3 examples do not obey the effective atomic number rule. That's why these are called as exception for the EAN rule. So we will calculate the EAN and then we will decide what is the effective atomic number. See this, we will take this example. We will discuss this example. Metal, one complex is given here, FeCN6 3 minus C. We will discuss this example. Fe, you know the atomic number of Fe is 26. This X indicates, X is the number of electrons lost when the atom, this metal forms metal ion. So we have to calculate the oxidation state of this Fe. So 6 into minus 1, 6 cyanide ligands having, because this is anionic complex, it is having minus 1 charge. 6 into minus 1, it is minus 6. And these are the 3 minus. When these 3 minus came to this side, the oxidation state of Fe will be 3 plus 3. So 3 electrons will be lost. So X is 3. And there are 6 cyanide ligands. So the Y will be 12. So if you do the according to this formula, the effective atomic number is 35, which is not obeyed, which is not equal to the next rear gas. Means these 3 examples which do not obey the effective atomic number rule. Remember, this may be asked for board exam, very IMP. So make a practice at your home. Atomic number of this copper, I will discuss this example also. Atomic number of this copper is 29. See, ammonia ligands are neutral ligands. Again, 4 into 0 will be 0. So the oxidation state of copper will be again plus 2. So X is 2 and Y will be 8 because 4 ligands donate 8 electrons. So 29, 2 and 8 according to this formula, we'll get the 35 here. Then another one example is given, platinum NH3 4. Again, there is a neutral ligand. So the atomic, oxidation state of platinum will be again plus 2. But see here, the atomic number of platinum is 78. This will be given, don't worry, for the board exam, these atomic numbers will be given on the first page. If it is not given in the example, remember in the instruction, below the instruction, these atomic numbers will be given. So this is a 78, 2 and 8. You will do the addition and subtraction, we will get these values. So effective atomic number and EAN rule is very important for the board exam, remember. Then we will start, the next part is isomerism in coordination compounds. Isomerism, this word in 11th standard, we already know what is meant by isomerism. The compounds having the same molecular formula, but arrangement of atoms is different. It is called as isomerism. So such type of isomerism is also present in coordination compounds. But this isomerism is quite different. I will explain with the help of this chart. So isomers, there are mainly 2 isomers. One is a stereoisomers and another one is a structural isomers. So stereoisomers we will discuss. These stereoisomers again, these are classified into 2 types. One is a geometric. Geometric isomers are also called as diastereomers. Remember, this word is not familiar with you, but for the board exam, this word they are using. Examiner particularly use these words, diastereomers, because student knows geometric. So for the board exam, they will make quite confusion. So remember this word, distereomers. Geometric isomers are also called as distereomers. And the second part of stereoisomers is optical isomers. Optical isomers you already learned in the chapter halogen derivatives, enantiomers. This term already you know what is mean by this enantiomers. Then this geometric isomers, again these are classified in trans isomers and cis isomers. What is mean by trans and what is mean by cis in 11th standard also in the chapter alkene, we learned the basic information about this. In detail, we will discuss in this coordination compounds, isomers. So this is the classification of stereoisomers. Stereoisomers are classified in geometric and optical, and then again the geometric are classified in trans and cis. Now I am coming to these structural isomers. As the name itself suggests, depending upon the structure of the isomers, this classification is done. First one is a linkage. Depending upon what type of linkage is present, these are the classified. Again, second one is ionization, third one is coordination, and next one is solvent. So all these isomers one by one we will discuss. So first one is stereoisomers. What is the stereoisomers? I will explain first. Stereoisomers having the same connections among the constituent atoms. So this word is very important. I will explain. These isomers having the same connections among the constituent atoms, but in the space, their arrangement is different. Their arrangement is different. That's why these are classified in geometric isomers. Geometric, just I told you, geometric isomers are also called as distereomers, and the second part is enantiomers. This is due to their arrangement of the atoms in the space is different. So we will discuss first what is meant by geometric isomers or distereoisomers. So these geometric isomers are non-mirror image stereoisomers. Remember, these are non-mirror image stereoisomers. These are possible in heteroleptic complexes. Yes, this is very important. Homoleptic complexes do not show the geometrical isomerism. We already learn about heteroleptic means two or more different types of ligands are involved. This is called as heteroleptic complexes. And when same types of ligands are involved, this is called as homoleptic. So these geometrical isomers are possible only in heteroleptic complexes. Heteroleptic complexes are the complexes in which more than two types of ligands are involved. Means, for example, if ammonia ligand is there, then chlorine ligand is there, like this. And homoleptic complexes means only one type of ligands are there. For example, only if ammonia ligands are there, it is homoleptic. And if more than two ligands are there, more than two types of ligands are there, this is heteroleptic. So remember this heteroleptic complexes, because this may be asked for the MCQs for geometric isomers. Which of the following types of complexes shows the. So remember this answer, heteroleptic complexes show geometrical isomers. Again, you know this geometrical isomers having the two types is cis and trans isomers. So what is cis and trans? In case of alkenes, the definitions are different. Now we are discussing the isomers, the definitions are different. So what is mean by cis isomers? The identical ligands occupy the adjacent position, remember. Identical ligands, they occupy the adjacent position, and in case of trans isomers, identical ligands occupy the opposite positions. So after example, these concepts will be clear. What is mean by cis isomer and what is mean by trans isomer. So these cis and trans having the different properties, remember. This cis and trans isomerism is observed only in case of square planar, remember. Square planar and octahedral complexes. These cis and trans is not possible in tetrahedral complexes, remember. This may be asked for MCQs. So we will discuss the square planar complexes. Square planar complexes, the coordination number is 4. So what is this square planar complexes? See how many, this is one general type of complex, Ma2B2. This M indicates the central metal atom, this A and this B indicates these are the ligands, A2 and B2. These are the ligands. And another type is given here, Ma2BC. This M again indicates it is a metal. This A is ligands. This is the ABC. These are the monodentate ligands, which is mentioned here. Where A, B, C, these are the monodentate ligands, and M is metal. So this is the general complexes are shown. We will take one example. See this Ma2B2. See, this is a Ma2B2 type of complexes. M indicates here platinum is metal. A2 means there are two ammonia ligands, and B2 means there are two chlorine ligands. So this complex is Ma2B2 type of complex. So I think A2 and B2 concepts are clear. A2, this is a monodentate ligand. This chlorine is also the monodentate ligand. Now see this example of cis and trans. This is important. See, according to the definition of the cis and trans, see identical ligands. See these identical ligands, chlorine, chlorine, identical ligands, ammonia, ammonia, these are the identical ligands. So according to the definition of cis, identical ligands having the adjacent position. So these having the adjacent positions, NH3, NH3 also having the adjacent positions. And see these trans isomers, according to the definition of the trans, see the definition once again. I want to give the definitions. Identical ligands occupy the adjacent positions in case of cis, and in case of trans isomers, it is clearly mentioned identical ligands occupy the opposite positions. So see this example. See, identical ligands occupy the opposite position. This chlorine and these chlorines are opposite side. This ammonia and this ammonia clearly we can see at the opposite side. So this is a trans and this is a cis isomers according to the definition. This is Ma2B2 type of complex. Now we will discuss this Ma2BC. See, this is Ma2BC. This B is different ligand, C is different ligand, A and A2. This is a different ligand. So Ma2A2. So this ammonia is single. This may be B. This H2 is C, and this Cl2 means A2. So this ammonia is different ligand, H2O is different ligand, then Cl2 is different ligand. So there are three different ligands in this. So the complex is like this, Ma2BC type. A2 means there are two monodentate ligands are there, same, and BC, these are the different ligand. So if such type of complex is there, according to the definition, you know, identical ligands having the adjacent position. So Cl is having the adjacent position, and there is a H2O and NH3, and identical ligands having the opposite position. So this is a example of trans isomer, and this is example of cis isomer. So I think the cis and trans concepts are clear. These are the examples in case of square planar complexes. Now these properties of cis and trans isomers are completely different, remember. So the cis isomer is more, so we were discussing this. This is a cisplatin. This is a cisplatin. We are discussing the properties of cisplatin out of the cis and trans. This cis isomer is more soluble in water than this trans isomer. Also, the cis isomer is called as a cisplatin, which is anti-cancer drug. While this trans isomer is non-active. It is a biological non-active. It is a physiologically also non-active. See this different. See this difference. If these chlorines having the adjacent position, this work as an anti-cancer drug. And when these two chlorines are the opposite side, it is biologically non-active also and physiologically non-active. See it is the magic of the chemistry. Though the molecular formula is same, but the arrangement is changed, all the properties will be changed. So this is a very miracle in chemistry. See, This cis isomer is polar with a non-zero dipole moment. See, this is the cis isomer is polar, which is having non-zero dipole moment, and the the trans isomer. This is a trans isomer which is having the zero dipole moment. So these properties we discussed. This is more soluble, and this is a work as an anti-cancer drug. So remember, these properties may be asked for 1 mark for the board exam. Write the properties of cis and trans cisplatin. So remember, this is a 1 mark question. For the 1 mark, this can be asked. So this is for only understanding why the properties are different. So these properties are given here. But remember how the cis isomer is drawn, and why the how the trans isomer is drawn. This arrow indicates this ammonia. This ammonia donates lone pair of electrons to this platinum. So this arrow indicates the bond is formed between the metal and ligand. So as the lone pairs are donated from this, so the arrows are shown inside towards the platinum. So again, the next type is cis and trans isomers in octahedral complexes. Now you know, in octahedral complexes there are 6 ligands are there. So we'll again discuss there are 2 types of 3 types. We will discuss there are 3 types of complexes. First one is A4B2, MA4B2, and then again MA4BC, MAA2B2. We'll take an example, then it will be clear. So this AA is a bidentate ligand. Remember here, this AA is bidentate ligand because AA2. This is shown AA2. AA is bidentate ligand. When single A is there, it is monodentate. When single B is there, it is monodentate. When single C is there, it is monodentate. When double it is AA is shown, it is a bidentate ligand. Remember. So these octahedral complexes, there are 3 types of octahedral complexes we will see. First one is MA4B2 complex. Second one is MA4BC complex, and third one is MAA2B2. These complexes we will discuss first. See, this is MA4B2 type of complex. M indicates metal, A4. See, this is the A4 means there are 4 monodentate ligands. See, 4 ammonia. See here, 4 ammonia. These are the monodentate ligands, and there are 2 chlorines. That's why the B2 is shown. So according to the definition of cis and trans, we can clearly see here in case of octahedral complexes. See, these having all the ammonia having the identical position. See, this is NH3, 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 NH3 having the identical positions, and we can see clearly these are the chlorines also having the identical positions. So this is MA4B2 type of complexes, and this complexes is octahedral complexes. Why octahedral? Because we can calculate 1, 2, 3, 4, 5, 6. 6 ligands are attached to the central metal. So the coordination number is 6. That's why it is octahedral complexes. But we can see here in case of trans isomer, see these are the opposite sides. We can see this is up. As there are 4 ammonia ligands are there. So 1, 2, 3, 4. These are kept as there is no possible way, different way. So these 2 chlorines having the opposite side. These 2 chlorines are placed in opposite side, and these 4 ammonias, these are in one plane. 1 chlorine is above and 1 chlorine is below. So this is MA4B2 type of complex. Then we will discuss the another type, MA4BC. This one, A4BC means the B is a different ligand and C is different ligand. C. This 4 ammonia is A type. BC chlorine is different, and this bromine is different. So in case of cis isomer, see this. the position of the 4 ammonia. This is adjacent 1, 2, 3, 4 having the adjacent position, and this is a chlorine and bromine. And in case of trans isomer, so again same type, same like this Ma4, Ma4B2 type. This is a chlorine and bromine having the opposite. These are having the opposite directions. Chlorine and bromine are the opposite direction, but these are the different ligands. Chlorine and bromine having the different ligands, and these 4 ammonia we can see this. These are also having the see, one NH3 is here, another NH3 is here. So there are they are also kept at the opposite sides. Then we will discuss the third type of this one. Third type is MAA2. This is a bidentate ligand. Remember this one, MAA2B2. This such type of complex is one example is given here. This complex is ethylene diamine. You know, this ethylene diamine is a bidentate ligand. So we are using here 2 ethylene diamine. So that's why it is shown here AA2. AA2 indicates this is ethylene diamine is a bidentate ligand, and B2 means any B type ligand. So chlorine is shown here. So this is a cis isomer and this is a trans isomer according to the definitions. See, the identical ligands are into the adjacent position. See, the position is adjacent, and in case of trans isomer, the identical ligands having the opposite direction. See, this EAN opposite and this CL is opposite. So out of these examples, any one example can be asked for the board exam. So we will discuss the next part of this stereoisomers is optical isomers. In enantiomers, I will take it first because already we discussed this in detail in the chapter halogen derivatives. These are non-superimposable mirror images are each other. They are having the chiral carbon. Chiral carbon is nothing but which is having the 4 different groups. So these enantiomers, there are 2 types of enantiomer, dextro and levo. When the plane of plane polarized light is rotated to the right hand side, it is called as dextro, and when it is the plane of plane polarized light is rotated to the left hand side, it is called as levo isomers. So these already we discussed in detail in the chapter number 10. So directly I will show how these isomers are looks like, how these isomers looks. So again there is a CO EN thrice. Again there is a bidentate ligand. There are 3 ethylene diamines. See, 1, 2, 3 ethylene diamine. If it is a D, automatically it will be L, because these are non-superimposable mirror images of each other, and we know enantiomers they rotate in opposite direction, but the angle is same. If it is rotated 30 degrees to the right hand side, it will be also rotated to 30 degrees to the left hand side. Means the angle is same, but the direction is different. So these are called as enantiomers, remember. So these are the optical isomers in octahedral complexes. These are the very good example. Ethylene diamine, tris ethylene diamine cobalt 3 plus. So these are the mirror images, non-superimposable mirror images of each other. We can see here clearly, because if this is put on L, if it is put on D, this will not match. These are non-superimposable mirror images of each other. If it is D, it will be L. If it is D, automatically it will be L. So next part is these octahedral complexes existing as both geometric and optical isomers, but in this type only cis isomers exist. See, this is octahedral complexes. This is octahedral complex. In this complex only the cis isomers exist.